Hello everyone, welcome back to another video of Maths 215. In this video, we shall be discussing the concept of antiderivatives in the case of complex variables. So, I'm sure in Math 120, you learned about antiderivatives. And in general, say you have a function f of x. Now, I'm just doing it for the real number variable. Here, f of x, and if you take the first derivative with respect to x, okay, I denote it as small f of x. And if you were to integrate that small f of x, as in the first derivative of x with respect to the first derivative of f with respect to x, you integrate f of x and take any interval a, b over dx, you would simply get this original function that you had first taken a derivative of. Basically, the rule of antiderivative basically tells you that integration is the opposite of differentiation and differentiation is the opposite of integration. Okay? I won't be going into the proofs for that, but I'm just going to state it. Now, moving on to our case of complex valued functions. Okay? In the case of complex valued functions, the integration, in general, you'd have a function of f of z, integrated the element of integration being z over a contour. The result of the integration will heavily depend on your choice of contour. But there are cases where you will find that regardless of the choice of contour, you will find the same result. And that is when we use the trick of antiderivatives. But you can only use the trick of antiderivatives for a few integrals, given you have to satisfy a few theorems, okay? And I shall be stating those theorems and subsequently giving you examples of how to use those theorems into getting your results. Okay, so are we able to theoretically use the option of taking antiderivatives? Only when the integral is basically independent of the path. And yeah, I'll go into the theorems which tell you when you can use the antiderivative trick. So suppose you have a function f of z which is continuous in some domain D. Okay? Continuous is the key word here. Your function has to be continuous in your domain D. Then, if any of the statements are met, then you can use the trick of calculating using the antiderivative. One of those theorems that you have to maintain is the fact that f of z has to have an antiderivative f of z throughout domain D. Okay? The next part, B, is the fact that the integrals of f of z along contours. Here, the contours must lie entirely on D, cannot be exterior to D, D being our domain, lying entirely along contours, lying entirely in our domain D and extending from any fixed point z1 to any fixed point, these points being your limits of your integrals, to any fixed point z2, all would give the same value for the definite integral, okay? Definite integral. Now, it isn't important for you guys to memorize these things. When I'll be giving you the examples, all your problems, or it will be common to the examples that I give you. So you don't have to be memorizing all of these theorems and all of these corollaries and everything. Don't worry, these are pretty simple. These might look very complicated, but they're pretty simple to understand when you start using it. Integrals will have the same value. Okay, I'll just erase this part so that I can write what this theorem actually does mean. The definite integrals will all have the same value, as in this integral endpoint z1, z2 will give you f of z. Of course, your limits are z2, z1, and it's basically simple. That's what happens after this. I'll just go to the next line so that I can get some more space. Okay, now a very important part to note. Say, I'll draw it. So say, for example, you're asked to integrate a function f of z, okay? You're asked to integrate any function f of z, and you're asked to integrate it in a certain contour, okay? dz. Now your contour in your xy plane is a simple one, as in it's closed contour, okay? And of course, a contour, by tradition, it goes anti-clockwise, okay? So that's the direction. So this is your contour C. Now, since this is a closed contour, even if you look at the original sort of definition, if you see it in Shuvo's videos, how you parameterize contour integrals to simple looking integrals, and to integrate with respect to t with the parameterization, in similar manner, if you take it like to be a closed contour, the endpoints are basically similar, right? Yeah, because if you start from here, imagine you're here, okay, and you want to end somewhere. But well, basically this is just a loop, right? So wherever you start, you can basically end there, right? Go from here, and then you basically end here. So your endpoints end up being the same thing. And say you have a function f of z is equals to z, very easy function. And if your endpoints are similar, like say you take one of your endpoints to be 1, you start at 1, but then you'll be ending at 1 as well. Your 1 is here, you start here, and then you basically end up here. And then what your integral would look like is capital F of 1 minus capital F of 1, which is basically 0. So a very important statement this is the fact that the integral around a closed contour will always result in 0 if your function is analytic and continuous in the given domain that your contour is in. Okay, so given your function is analytic and continuous inside that contour, it will always result in 0. So just blindly give 0 whenever you see these kinds of problems. Thank you, and hope to see you again in the next video.